As we begin the final video of this specific playlist, video 35, if you've been watching from the beginning, I'd like to say thank you for tuning in and good job for sticking through the many hours of content. If you haven't watched some of the earlier lectures in the playlist, I'd encourage you to do so when you have the chance. In this particular lecture, we'll be discussing the topics of linear regression and multiple linear regression. This particular subject matter warrants a long runtime, as every scholar and researcher should be at the very least be able to successfully apply and interpret a regression analysis. The reason for this video being the last video in the playlist is the content presented within these slides is the culmination of a cumulative foundation of topics from prior lectures within the playlist series. As always, the code and data sets in CSV format can be found in the video description below. So what is linear regression? Linear regression is the term which is utilized to define a specific linear model which measures the relationship between a dependent variable and an independent variable. Once established, the underlying equation from which the model is derived can be further utilized to predict the conditional value of the dependent variable in differing situations. So the regression model format is above right here. And Y is our predicted values of Y, the predicted values of our dependent variable. B is the slope or rate of predicted increase or decrease for the dependent variable for each unit increase of X, X being the independent variable. Over here, we have the y-intercept value, which is the level of Y when X is equal to 0. A linear regression model, a basic linear regression model, is going to contain one independent variable and one dependent variable. And this model should remind you of the slope-intercept form. Maybe you encountered the slope-intercept form in a geometry class in your undergraduate, or maybe you encountered this in high school. But in any event, it's very similar in that we have y equals mx plus b, m being the slope, and b being the y-intercept, and x being the value of x in a given circumstantial situation. Now, there are other types of regression application. Those which immediately come to mind are ordinal and logistic. However, in this lecture, we're only going to be covering linear regression and then multiple linear regression. So let's say, for example, we are looking to create a model through the utilization of the linear regression methodology, which might potentially predict the number of points that a basketball player might score in a season. In this case, our points scored in a season is our dependent variable, or y, and we could potentially consider as our independent variables, we could consider height, we could consider weight, we could consider the time in which a player runs a 50-yard dash. And in such an instance, points, again, would be our dependent variable, and any one of these values would be our independent variable. Now, linear regression differs from some other concepts which were previously discussed at length in that the primary function that we're looking to achieve through the application of this methodology is we want to create a predictive modeling tool. Now, the case of linear regression, simple linear regression, our model will only contain one dependent variable. In this case, y will be our dependent variable, and x will be our independent variable, because with linear regression, we're only going to have one independent variable, one dependent variable. Now, as we go through these slides and get into multiple linear regression models can have any number of independent variables, but still only one dependent variable. So in this case, again, y is our dependent variable and x is our independent variable. So if we're thinking about a situation as it pertains to predicting points for an individual basketball player, y would be the points scored per game, perhaps. And x could be something like a 50-yard dash time. And we're not just thinking about this in terms of a single basketball player. In this case, this would be the points scored by one single basketball player in a season and their 50-yard dash time going into the season. Points scored by another basketball player in a season, their 50-yard dash time. Third basketball player points in a season, their 50-yard dash time. Obviously, these numbers are not indicative of those values, but it would still, as far as application methodology is concerned, it would still be the same methodology. But in this case, we're just using values of X and values of Y, and they can represent whatever we'd like. So you'll likely never have to do this, but just to appreciate what is going on as it pertains to model synthesis and associated components, we'll quickly walk through the creation of a model as it applies to the data which appeared in the prior slide. So we need to find these values here. So we have uppercase sigma x, uppercase sigma xy, uppercase sigma y, and uppercase sigma x squared. And what that is we need to find the sum of all the values of x, all the values which were contained, observational values of x. We're going to sum those together. So that's sigma x. We're going to sum all the values of y, all the observational values of y. We're going to sum those. That's sigma y. And then we need to find sigma x squared. And that is all the values of x summed. But prior to summing them, we're going to square them. So 27 squared, 34 squared, 22 squared, 30 squared, and so on and so forth. And the sum of those values squared is this value here on the right. We also need to have the sum of xy, and that is the sum of the product of each value, observation value of x, multiplied by its corresponding value of y. So 27 would be our x value, multiplied by the y value, the corresponding y value being 70. And then we would add that to the next observational bit of the series, 34 being our x value, 80 being our y value. So once we have the product of each, we would sum those all together and come to this value here. So 2770, 3480. If we go back, 2770, 3480, 2273, 3077. And you can see that it's each value and its corresponding associated value, the product of each summed. Okay, so now we have to find x bar and y bar. To do that, we take the values that we had derived previously, sigma x and sigma of y, and we divide each of those values by the number of observations in the series. So there were 10 observations, 10 x observations, and 10 corresponding y observations. So we take the value of sigma x and we divide that by 10. And we take the value of sigma y and we divide that by 10. And we get the x bar and y bar values. And that is what has been achieved here. Now we have to find the slope. And to find the slope, we have to perform the following equation. So in this case, we have sigma xy, which was previously derived. And from that, we're going to subtract n multiplied by x bar multiplied by y bar. And from this calculation here, we're going to divide this calculation by the value of sigma x squared, which again was previously derived. From that, we're going to subtract n, which was 10, multiplied by x squared, parens, squared. So this is number of observations, parens, x bar, squared. All right, and that will provide us with the slope. So if we were to input all of the values to complete this formula, it would resemble this. So this is our slope value. And now finally, we can derive the linear regression formula by solving the equation below. So y, therefore, is going to be 78.5 plus 0.8509235 multiplied in parens by the value of x minus 30.4. So when we work that all out, it comes to these values here. So therefore, our value of y equals 52.63193 plus 0.8509235x. And now we have our linear model. And from this, we can predict outcome data. So here are our slope values. All right. And over here, this is our intercept value. Okay. So our intercept value is not going to change, nor are these slopes. But to get our predicted outcome, our predicted y outcome, we need to enter a corresponding value of x. So if we put x into this equation, it would be 27, value of x, multiplied by the slope value, which is, we're just going to round this off to three significant figures. We'll say 0.851. All right, we'll round that to three significant figures. So 27 multiplied by 0.851 plus, we'll round this also to three significant figures, 52.632. And if we add those values together, we get 75.6. If we do the same for this next value of x, 34, we multiply it by 0.851. And then that product, if we add that to 52.632, we get the value, predicted value, of 81.56. And that's what you're seeing here. So in this case, we have the predicted value of y from our model. These are the original observations of x that we utilized to create our model. And these are our original observations of y, which we also utilized to create our model. So you can see the differentiation as it pertains to the predicted value of x, or excuse me, the predicted value of y given x as measured against the actual corresponding observation of y. So our initial observations, we had 27 as our x value and a corresponding observation of 70 for our y value, 34 for our x value, corresponding observation of 80 for our y value. In the case of our model, a value of 27 for x gives us a value of 75.6 for y. And again, you can see the differentiation between the predicted y values and the actual y values from our original observations. Now, if we were to graph our linear regression line, it would look something like this, and I'll show you how to create this momentarily. But what we have here as far as the dots are concerned on our graph, these dots represent a x value and its corresponding y value. So these were the observations from our initial values of x and y, which we put into the equation to create our model. Okay? So this was the X value and corresponding Y value for each observation that we utilized for model creation. And this dotted line here, this dotted line represents a perfect predictive model. So in every case, if we put an X value into our predictive model and came out with a corresponding Y value, our dots from our initial observations would fall on this line, because this line is the model assuming that a perfect prediction of Y is given for each observation of X. So if the dots fall far off of the line, that would typically indicate that our model is not very good. And the closer that they fall to the line, that would indicate that our model is actually pretty decent. So again, these are our observation or observed corresponding X and Y values from which the model was created. And this dotted line represents a perfect model. Now, we were going to work through the math to assess the strength of the model's predictability. We would use this formula here. And once we go through all of how the math is actually formulated, the different aspects of the model, we'll do the example and a subsequent example for multiple linear regression in RCommander. But in the interim, let's assess the strength of model predictability. So to assess the strength of the model's predictability, we must solve for the model's corresponding coefficient of determination. And that is the R squared value. So R squared is the symbolic notation which represents the coefficient of determination. And this can be achieved through the utilization of the equation below. So here is how that math is completed. We have the sum of y squares, and that is sigma y square. And that's just the value of each y observation squared and summed. And then this is how the R square value or coefficient of determination is derived. As you can see, you have to put the sigma y square value in as a component to derive the coefficient of determination, or R squared. And let's just talk a little bit more at length about the coefficient of determination, because it's a very important concept. So the coefficient of determination, also known as R squared or simply lowercase r squared, can be thought of as a percent. It gives you the idea as to how many data points fall within the results of the line formed by the regression equation. The higher the coefficient value, the higher percentage of points the line passes through when data points and the line are plotted. Now, in most entry-level statistics classes, this is the only variable that is evaluated when determining model significance. Typically, the higher the value of the coefficient of determination, assuming that all other tests of significance are met, the greater the usefulness and accuracy of the model. And this value, the R squared value, can be any number from 0 to 1. A value of 1 would indicate a perfect model, meaning that all the points on the graph fall on the dotted line, and a value of 0 would be a completely imperfect model. So let's do linear regression now in RCommander. And again, the data for this example that we're doing is in the video description below in CSV format. So we're going to assume that you've already imported that data into RCommander. And with RCommander's menu up, you're going to select Statistics, Fit Models, Linear Regression. Now from here, you're going to select a response variable and an explanatory variable. So we have it perfect in that our response variable, or dependent variable, is going to be y, and our explanatory variable, or independent variable, is going to be x. Now, if this were the case for our basketball player, you might have different variable names, in which case, instead of y, you would select points, and then you would select whatever variable is the independent variable which you're utilizing for your model. It could be 50-yard dash time, height, weight, etc. But in this case, it's just a perfect example. So we're going to select y as our dependent variable, x as our independent variable, and then we'll click OK. So this is the output that is provided to us in our output window of RStudio. And we've got a bit going on here. We have our values to the left and our values over here to the right. And we have our multiple R squared, or coefficient of determination. So let's go over each bit of output, and I'll show you also how to report your findings in APA format, and also how to build a model. So the p-values, as it relates to the output, this value is the corresponding significance pertaining to each variable within the regression model. This value can serve as greater importance when performing multiple regression analysis, as you'll be looking at the significance of each particular variable in the model. R squared, or coefficient of determination, is going to help you determine the model strength. And a way to remember R squared is it's the explained variation divided by the total variation. This value is always going to be between 0 and 1, or 0% and 100%. So let's state our findings in APA format. We're going to state that a linear regression model was utilized to test if variable x significantly predicted outcomes within observations of y included within the sample dataset. The results indicated that x, and these are the values taken from the output, this is our p-value, okay, is a significant predictor variable, and the overall model itself possesses a somewhat worthwhile predictive capacity. Predictive capacity is going to depend on the R squared value, the coefficient of determination. Now, typically you'd prefer an R squared value above 0.5, but really it depends on the circumstances, what it is you're modeling, and what you're looking to achieve with the model. But sort of rule of thumb as it pertains to Stat 101 courses is you want to have a predictive capacity greater than 0.50. And in a perfect world, you'd prefer that every variable within your model, as it pertains to variable significance, be lower than an alpha value of 0.05. So the p should be lower than 0.05 in a perfect world for every variable included within the model. So let's build our predictive model from what was provided within our output. So we have our intercept value here. We're going to place that last. So our intercept value is going to be static. Here is our slope value for x. That's 0.8509. And the p-values, you only report those in APA and utilize them to determine whether or not model variables are significant or otherwise. They're not utilized in creating the predictive model. So here we have our model in action. We looked at this in a prior slide, but as you can see here, we have our x values, our original observed values of x. Our intercept value is not going to change. It's going to be the same as far as the equation's concerned. It's not going to change as it depends on the observation. And with this particular equation here, you can use Excel or you can use pencil and paper to test your model to see what the outcome variable is for y, the predicted outcome variable y, is as it relates to our value of x. And remember, y is our dependent variable, and x is our independent variable. So here, as you can see, with a value, an observation value of x being 27, we would multiply that value, 27, multiplied by 0.8509, and we would then add the intercept value of 52.6319, and that would give us the predicted value of y. In this instance, if we have a x observation of 34, we will multiply 34 times 0.8509, and then we would add the value of 52.6319, and that would give us the predicted value of y. Last one, 22, we would multiply that by 0.8509. I'm going to multiply that by 34, all right? Because in that case, that is our x value. Then we add the intercept value, which is 52.6319, and we get our predicted y value. Okay? So whatever the value of x is from our initial observations, multiply that by the associated slope, and then add the intercept value, and that provides you with the predicted value of y. Now, unfortunately, RCommander does not possess built-in functionality as it pertains to model predictability, testing, and results. So you'll need to run some variation of the code depicted in this slide and the subsequent slide in order to achieve this. And you can do this bit of code. You could either put it all into the RScript portion of RCommander's menu and submit it, or you can just put it directly into the RStudio console and submit it there. And this code is in the video description. So you'll have to create the model again. Function lm is going to build the model. You're going to need to specify the dataset name and then use the $ to specify the dependent variable and independent variable within the equation. The next bit of code will create a new data frame which contains the independent variable values from the prior model. That's right here. You can then use predict to create output, which contains the results of running the initial independent variable values to the model equation, thus creating the dependent variable values related to such. And this final bit of code here, this stores those predicted values. And then if we wanted to add the original values of y to that data frame so we could compare predicted values against the actual observed values for the dependent variable, we would run this code here, and then we could view the results. And this is our output in each instance. This is what the code is going to look like as it executes and creates output in your R console. And as you can see, these are the actual observed values of y, and these are the predicted values of y. They're also up here, but not as evident as when you run through the entirety of the code and can view them in this manner. Now the code in this slide must also either be run in the console or within RCommander's menu portion to create the regression line output. And you would need to change this to what suits your needs. This creates the initial plot and ab line line regress creates the predictive line. So let's move on to multiple linear regression. Multiple linear regression is essentially just linear regression with multiple independent variables. And it can be defined as linear regression, which contains multiple independent variables. And like the linear regression model, it contains only one dependent variable. So one dependent variable, multiple independent variables in this case. So if we're compiling this by hand, the formula for this model would resemble the following. And as you can see in this case, we have multiple slopes and multiple values, which are going to be input to create our predicted dependent variable. So in this instance, for a multiple linear regression analysis, we have a couple variables. We have W, X, Y, and Z. And each one of these is corresponding observations. So if we return to our basketball example, this could be the number of points per season for a single player. This is the height of that player, the weight of that player, and the time in which the player runs a 50-yard dash. This would be the points for the next player, height, weight, 50-yard dash, and so on and so forth. Each one of these variable values would contain corresponding observational measurements. So let's create in RCommander a multiple regression model with the data provided. CSV is in the video description below. With it imported from RCommander, you will go to Statistics, Fit Models, Linear Regression. In this case, we only have one dependent variable, but we have three independent variables. So make sure you select all three or any independent variables that you're going to utilize as it relates to model creation. Once that's done, click OK. If you used the data set in the video description, you should receive output which resembles this output here. Here is our coefficient of determination. Here is our intercept value. Here are our slopes. And here is the p-values, which correspond to each value within the equation. And as you can see here, we have the slope of variable W, the slope of variable X, and the slope of variable Z. Remember, Y was our dependent variable. And as a reminder, p-values are the values which indicate the corresponding significance of each variable pertaining to the regression model. And values which are less than 0.05 as it pertains to each variable value are typically believed to indicate a variable which is significant. The significance determines the level of impact that a corresponding variable has in determining the value of the model's dependent variable. So p-value, it is important to indicate that removing variables simply on the basis of p-value will not necessarily improve the strength of a model. This occurrence is inhibited due to the impact that each variable has in tandem with each other variable within the model. So adding and removing variables from a regression model based on p-value or intercept value doesn't always necessarily strengthen a model and will change the p-values of the variables contained therein. So as you can see in the top model, we only have 2 independent variables, and in the bottom model, we have 3 independent variables. And in each instance, we have a different multiple R-squared value. And in each instance, the p-value of the independent variables shifts depending on the inclusion of other independent variables within the model. So it's important to know that the more observations that we possess as it pertains to model strength, as we synthesize the model, the more robust we can say the strength of the model is, or the more robust we can predicate our assumptions upon. So again, if we start making changes based on slopes and significance alone, it doesn't necessarily lead to a stronger or weaker model, because the significance of those variables within the model, as well as their slope value, depends on the inclusion of the other variables within the model. So in this instance, we're going to build our model with 3 predictive or 3 independent variables, 1 dependent variable being predicted, that being y. So w, x, and z. All right. And if we assembled the predictive model from the output, we would receive the following. And we could test this in Excel or with pencil and paper by doing the following. The observation of W multiplied by 0.402, the observation of X multiplied by 0.450, the value of Z multiplied by 0.131, added to the value of 0.36.528 in every instance, the intercept value. And that would give us the value, the predicted value of our dependent variable, y. And these values are just coming from our original observations. And those slope values are coming from our output along with our intercept value. And if we were going to run code to check the outputs of our dependent variable against the original dependent variable observations, you would have to run some sort of modification of this code, which is again in the video description as it relates to your data frame name, the number of variables that you're going to include as far as independent variables are concerned within your linear model. And you can use this code within the console or within the console menu portion of RCommander. So a couple of conclusions. R squared is the model's corresponding coefficient of determination. It's the explained variation divided by total variation. R squared is always going to be between 0 and 1, or 0% and 100%. This value is often utilized to determine the overall strength of the model. A multiple linear regression model can be defined as a linear regression model which contains multiple independent variables. And p-value indicates the corresponding significance of each variable pertaining to the regression model. Values which are less than 0.05 are typically believed to indicate a variable which is significant, and removing a variable simply on the basis of p-value will not necessarily improve the strength of the model. So that is it for this particular lecture. Thank you for watching until the end, and remember that all code and associated datasets can be found in the video description below. I'd encourage you to check out some of the other videos in the playlist if you're interested in building mastery. And with that, I wish you all the best of luck as it pertains to your coursework and your studies. Please consider liking and subscribing so we can get the word out to as many viewers as possible. All the best in the interim, and take care.